Hey guys, thank you for watching this lecture. This is our eighth lecture. It's going to be about chapter 3, properties of pure substances. And I'm going to solve the second example for you here um, in Blackboard. So in content, lecture material, lecture examples, number 3. So here I'm going to solve the second one, number 2 for you, a piston cylinder device. And please keep this in front of you on your screen because I'm going to refer to some informations and numbers which are provided in the text. So in my notebook. Well, so let me first read the whole example for you because as I told you before, we need to imagine the whole story in our mind in the beginning. So the question says, a piston cylinder device initially contains 50 liters of liquid water at 40 degrees C and 200 kPa. Heat is transferred to the water at constant pressure until the entire liquid is vaporized. Show the process on a TV diagram with respect to saturation lines. And it asks for A. What is the mass of water? B. What is the final temperature? C. Determine the total enthalpy change. Great. As we know, okay, so example number 2. As we know, in the beginning, we need to um, specify our system. What are we going to talk about? So as we saw in the text, it's all talking about a piston cylinder. It's closed, and there's like water in it, and then the water evaporates. So the system will be the piston cylinder content, which is the water. We need to know the material because um, it helps us to go to the specific table which provides the informations about the properties. And the question should say questions are mass of the system, final temperature, and enthalpy change. Keep in mind that we need to draw the process on a TV diagram at the end. So that's like the fourth part. So once again, we're talking about specific amount of mass, which is the content of the piston cylinder device. Therefore, it reveals that the system is closed. Because there is no mass transfer and it is a control mass. And also in control mass we know that all the boundaries are real. Great. Well, so let's draw the system. Here is the cylinder walls, and then we have the piston, which is free to move. There are no stops, no spring, nothing. It just basically it sits on the gas, whatever, which is pressurized underneath. And the content is our system. And we are adding heat. Okay, as I told you before in the previous lecture, when we are talking about a process, which is here like heat, it says heat is transferred to the water at a constant pressure. So we're talking about we're talking about a process, and this process, it's it has two states, the initial and the final. So we need to know exactly what are the properties of the matter, the water, at these states. So we need to identify the process states. At the beginning, we call that point 1, which is our initial state. Material, again, we need to know the material to go to the corresponding table, is water. And it says a piston cylinder device initially contains 50 liter. So volume is 50 liter in the beginning. Temperature is 40 degrees C. And we know the pressure as well, which is 200 kPa, kilopascal. Great. And now, basically, like these steps are just a summary over the whole example. So now I need to know what are the properties, what do I know, what's known according to the question. So at point 2, which is the final state, it helps you to get this summary, write this summary, just to make everything clear for yourself, that what you know, what you don't know, and what you need to know. I mean, yeah, and then it leads you through the solution. The material is water still, but there's a plus here because it says the status of the water. It says heat is transferred to the water at constant pressure until the entire liquid is vaporized. So we need to pay attention that as we warm up this water, it evaporates, and on the plot, we're going to have a mixture of vapor and liquid, and we keep going on, we keep adding this heat until we get no liquid state, and the liquid is gone. At that point, we have saturated vapor. If we keep on, and if we add more heat, we're just gonna basically warm up the vapor, and we will end up with like superheated vapor. But in this example, we are not doing that. We stop adding heat as we get to the state, to the fact that the entire liquid is vaporized. So it means that the state is saturated vapor. Helps a lot. This helps a lot because it tells us basically everything. If we know temperature or pressure only at this point, with knowing that it's saturated vapor, we're going to find all the properties on the table because we know exactly what is the status. Anyway, so, but here the volume, we don't know anything about the volume because now everything is vaporized, it expanded, and the volume should be something larger than 50 liter for sure, but we don't know how much it is. And likewise for temperature, we don't know anything about temperature. Now everything is at the higher temperatures, it's warmer, but it doesn't say anything about temperature. The only thing that it says is that the process that we went through is a constant pressure process, which means that the pressure at the final state should be equal to the initial state, right? because here on top it said that it's at 200 kPa. So let me put a note here that at a constant pressure, right? Which means that P1 equals P2. This is what is given in the example. The trick in solving thermodynamic problems was that we need to make a table for ourselves which summarizes basically all the information. I'm telling you all the information that are provided, all the information that is provided in the example, and also what we will calculate it. We will have a summary of everything that we have here. So, and this table is like this, that it says point 1. Here we have only 2 points. In future, when we go solving for compressor, turbines, we're gonna have like a process consisting of like 5 different points. That would be a huge table that we need to go through. Anyway, so now here it's simple. So I'm gonna just repeat all the informations. 50 liter. Temperature it helps a lot. Although it looks like something that it's not needed, but it is important to have it in our solution. Anyway, so everything in black, it's known in the text. I'll add what I will calculate in red for you. So P2, everything in black is known. So P2, it says that 200 kPa, it's just saturated vapor. That's all I know, according to the example. Okay, great. Now let's solve it. The first question, let me go to the next page. The first question is mass. We need to find the system mass. System mass. How much is it? If I scroll up to this table, I see that at point 1, I have pressure and temperature. And I know that at thermodynamic processes, at different states, I need to know only two intensive properties of my system. And here I have both of them. I have pressure and I have temperature. So I can judge on what the status of this point is, right? If I go to the table and I find these two pressure and temperatures, I can realize that if it is a mixture of vapor and liquid, if it is compressed liquid, if it is superheated vapor, I can realize, right? So let me write this for you. Put a note here. according to table A4 or A5. And why do I take this way? Why am I emphasizing on point 1? Why don't we use point 2? Because we're looking for mass. And we know that in all our tables, we have specific volume, the little v. You remember? Little v was volume over the portion, the volume over the ratio of volume over mass. And I'm looking for mass. And at point 1, I have volume, and it's just point 1. I don't know the volume at point 2. So I can take advantage of these two properties, temperature and pressure, and then realize the status of the matter. Then I can find specific volume, little v, sub 1, and then use that and this v1 to find the mass. So this is the idea. This is what we're gonna do. So if I summarize that for you, it means that we can find v1. Then we know that v1, capital v1 over little v1 equals mass. Then we can find mass, and then that's it. So according to table A-5, let me bring this up for you. So I add that on our blackboard. Here's in the 8 sheet. I need to scroll down to A4. There we go. And rotate this guy counterclockwise and zoom in a little bit. That's fine. And oh, it's A5. So here, A4. So I told you that I have temperature and I have pressure. So according to table A4, I know that at that temperature, which was 40 degrees C, check this out. Here. At that temperature, the saturated pressure is 7. Oh, sorry. What did I write here? Because I can. Okay, A5. Okay, because I can use both. I'll tell you later. Let me go to A5. Okay. So at this pressure, 200 kPa, I know that the saturated temperature is 120.21, right? So if we compare the magnitude of that temperature, so let's say T1, which was 40 degrees C at this pressure, is much less than the saturated temperature at same pressure, which was, how much was it in the table? 120.21 degrees C. So at the same pressures, this temperature is less than that temperature, right? So it means that the matter, the water, is subcooled. It's cooler than a saturated liquid, right? Because we know that the saturated liquid at this pressure is supposed to be at that temperature, but it's at this one. It's 40, which is less. So we say it's subcooled or it's compressed. They are the same. So we conclude that we have subcooled or compressed liquid. Okay. In another word, if I check the other table, so or now if I check the other table, So there's just one difference between these two tables. A-5 in this table, on this table, the first column is pressure, then temperature. But at the other one, A-4, the first column is temperature. So they're just one table. They're the same. But I mean, like, these are like rounded numbers that it's like it depends on your convenience. If you prefer to, like, if you have like 40 degrees C, you can directly come here and then pick this number, for example, here. Or you can go to the other table and find 40 in between these two, 32.85 and 40.29, and then do the interpolation. But no one does this because we have all those numbers at that specific temperature already solved. Anyway, so according to the other table, 8.4, at 40 degrees C, this is the pressure. See, 7.3851. But the question says that at this temperature, pressure is 200. So it's compressed. It's squeezed, right? So P1, which is 200 kPa at 40 degrees C, is much higher than the saturated pressure at the same temperature. If the matter, like, assuming if it was saturated liquid, right? If it was saturated liquid, the pressure was supposed to be that magnitude, but now it's 200, which means we have subcooled or compressed liquid. Great. You can take a look at this. What is it? Tell me. Lecture number 6, page 15. Yeah, it talks about compressed liquid. Well, so according to that page number, we know that, therefore, now the properties that we were looking for. V1, little v1 equals Vf at 40 degrees C, not, let me write this in red because it's important, not Vf at 200 kPa. Sorry. Yes. Why? Because if you take a look at that page, it says the properties of compressed liquid, compressed liquid depend on temperature. Because the only difference between compressed liquid and saturated liquid is that this compressed liquid is just the pressure is higher, and it's basically incompressible, right? It's like we say it's compressed, but it's liquid. The volume doesn't change. The bonding between the molecules, between water molecules, do not let us to compress it, to squeeze them and decrease the volume. The only thing that changes the properties is the temperature. It's like a little bit complicated. It's about intermolecular forces and interactions. I don't want to go through that. I'm just telling you that whenever you deal with a compressed liquid, please keep in mind that all the properties should be based on temperature, not the pressure. Forget about the pressure. Pressure is there only to help us to decide that if or if not the liquid is compressed. Okay. But then when we go to find the properties, we need to pick the temperature. So we need to go to which table? This is the trick. So we need to go to table A4, right? Because take a look. I told you that at 8.4 we have all these temperatures here that we can use. If we go to the other one, we have the pressures. We're not gonna judge based on pressure, we're gonna judge based on the temperature. So if I go to this table at 40, here are all the properties that I was looking for. Oh my god, here. And we are looking for, do not get lost in the example. We are looking for specific volume to be able to find the mass, and we are looking for enthalpy because at the part C it asks us about total enthalpy change. So according to this table, I'll summarize that therefore little v equals Vf fluid at 40 degrees C. Again, it's on that specific temperature, not pressure, which is 0.001008 meters cubed per kilogram, and enthalpy H1 equals Hf at, again, 40 C, which is 167.53 per kilogram. It's per mass. Everything is per mass. So we were looking for. So now we have the specific volume. Now I can calculate for mass, which was V1 over V1 capital over little, and it's 0.05 meters cubed divided by what we just found. And here we're about to find mass, 49.61 kilogram. Perfect. Let's go to the second question. Final temperature. I'll finish this lecture as soon as I can. It's a little bit left. So the final temperature, which means I forgot something. At point 1, I found these two values that I'm supposed to add those to my table here. In your exam, please keep in mind that you need to do this, because again, when we go to more complicated questions, we're gonna use these values that we find. So we need to summarize them somewhere on our paper. 167. Okay, great. Now it asks for the final temperature. So here, T sub 2 is asking for the temperature. Again, if you look at this, we have the pressure, and we know that the status is saturated vapor. So we can go to which table? Do you remember which one of them was for temperature, the other one was for pressure? The second one is for pressure. So we need to go to table 8-5, and at this pressure we can find the values corresponding to saturated vapor. So we can find temperature, enthalpy, everything, right? So according to so at point 2, thank you, okay, At point 2, we know that we have saturated vapor at P2 equals 200 kPa. So according to table A5 was about pressure. T2 is gonna be, oh, sorry. T2 at that temperature. Oh, pressure equals T saturated, because we're talking about saturated vapor, right? So the saturated temperature, see, let me show you. A5 here, there you go, 120.21 temperature. This is the value that we're looking for. 200 kPa equals 120.21 degrees C. That's it. And the final part, total enthalpy change. We found 120.21. degrees C. Here we found H1, and if we find H2 as well, then we can find the total change. At that point, point 2, we have everything. We know exactly what point we are at. So we will go to that table, A.G-5 once again. So we found previously that H1 was something. So again, once again, table A-5. Why? Because we are at a specific pressure here, 200. So we're looking for enthalpy. These three last numbers are the enthalpies, and we are at saturated vapor. See, look at the top. So saturated vapor all the way down to here, 2706. Therefore, H2 at this pressure equals Hg, G means gas, at 200 kPa equals 2706.3. Everything is per mass. And please note that the question is asking for total change in enthalpy, so it's capital H is total. We need to multiply everything by mass, so M times H2 minus H1. And the first section was there asking us about mass just for here to help us. We know now, we found this before, to know that mass is 70, oh no, 70, no, sorry, 49.61. What was 70? Where did I get that from? Anyway, 2706.3 minus 167.53 kilojoule per kilogram. And we know, I love singing, 125,050 kilojoule. Am I right? Let me check it with this number. Yes. And at the very end, very end, let's draw. Oh God. Okay. The T and V. We know that the saturated line looks like that. Here we have saturated, on this line, vapor. On the other curve we have saturated liquid. And in between these curves we have the mixture of saturated, we have a mixture of liquid and vapor. At the left side we have subcooled or compressed, and on the very right side we have superheated. According to our table, once again, we started with compressed liquid, and we know that compressed liquid is somewhere on the left of the curve, like here, for instance. So this is our point 1. I refer you to check page 7 on lecture note number 6. Please take a look there and then come back. If you look there, you see that these constant pressure curves look like that. Look like then constant. Here is phase change. We are converting from saturated liquid to saturated vapor, and then again it goes up. Okay, and since we know that the whole process is a constant pressure process, we're going to travel exactly on this curve, on this green curve. So from point 1, and then we end up at saturated vapor, which is this point, this junction of the green curve and red curve. So all I need to do is just to connect these two numbers, and this is the procedure direction. We start with point 1, which is a subcooled or compressed status, and then we go all the way up to saturated liquid on a constant pressure process. Okay, constant pressure. So I go on the constant pressure from point 1 to a saturated liquid. Then we have just only a phase change, which means that the evaporation, right? So we evaporate the whole saturated liquid to saturated vapor, which is point 2. Thank you for watching this lecture again, and that's it. Thank you.